Hello, my name is Vamsi Krishna. Today we are excited to present our project on the performance comparison of Spark ML decision tree model to SciKit Learn ML decision tree model. The aim of our study was to explore and analyze the effectiveness of two parallel paradigms, PySpark and SciKit, in learn building decision tree models. My teammates are Pawan Sandesh, Venkatanag Priyanka, Renika Chaudhary are embarked on this investigation to understand the differences in efficiency and time between these implementations. By leveraging distributed computing in PySpark, we expected to achieve better performance on large scale datasets compared to scikit-learn. These are the content we're going to express in this presentation. Motivation. The objective was to determine which model is more accurate and effective for the task at hand by evaluating the models based on time and efficiency. I aim to support the selection of the final model for deployment. The results demonstrate significant performance differences, providing valuable insights into the strengths of each paradigm. I will discuss the metrics and reasoning behind choosing the optimal model, showcasing the credibility of our decision-making process. Next. The research aims to investigate the performance and time differences between implementing a decision tree using PySpark and scikit-learn. Our null hypothesis suggests that the Spark ML model leveraging distributed computing will outperform the decision tree model in scikit-learn. Conversely, the alternative hypothesis posits that there will be no significant difference in performing and time between the two approaches. By conducting a thorough evaluation and comparison of this paradigm, we seek to provide valuable insights into the effectiveness of distributed computing in enhancing decision tree models. Next slide. Now comes to the related work. Many research articles provided comparisons on different modeling techniques. Decision tree is used as a baseline model for many implementation, and distributed computing has gained more attraction in recent years, as well as the data structure used in this model has more impact on how model performs. Our work is dependent on these above statements discussed in the research papers from the reference pages. Now, my friend Sandesh will continue on this.
Thank you, Vamsi Krishna. So, welcome to methodology. I'm pleased to present our methodology for comparing the performance of different tree models using PySpark and scikit-learn. To ensure robustness, we selected a dataset comprising at least a million data points, allowing us to analyze the model scalability. Firstly, we implement the decision tree model using PySpark, leveraging its distributed computing capabilities to handle large datasets efficiently. Secondly, we replicated the same model using scikit-learn, which serves as a widely used baseline for comparison. To evaluate the time taken for model training, we conducted the extensive experiments on both implementations. Additionally, we assessed the performance of both models, considering key metrics such as accuracy, precision, recall, and reference score. Subsequently, we applied the trained models on both the test and find datasets to ensure to examine their predictive capabilities and generalization, and to draw conclusions. Regarding the dataset, um, this dataset consists of an impressive 1 million data points with 13 feature columns and multi-class variables comprising classes B1, B2, and B3. These datasets offer ample complexity of our analysis. A significantly advantage of these datasets of is absence of null values, ensuring data integrity and reliable comparison between the models. In our preliminary data analysis, we employed volume charts, explored the datasets, and identified potential hyperparameters that could affect our models. These visualizations provided valuable insights into the distribution and impact of each attribute concerning the classes. Furthermore, the charts highlighted that the attribute ash shows a little variation across all classes. This indicates that the ash attribute might not be a strong differentiator when considering the class level, and its impact on the overall analysis could be limited. From this slide, my friend Priyanka will take care.
Thank you, Sandesh. I'll take this from here. The transformation in PySpark plays a crucial role in preparing data for machine learning models. Two essential transformation techniques we are employing in our project is vector assembler and category encoding. Vector assembler is a PySpark ML. It is used to consolidate multiple input columns into a single input vector. This transformation is vital for feeding data efficiently into machine learning algorithms, as many models expect input in vector format. By assembling the multiple columns into a single vector, we can enhance the model performance and streamline the data preparation process. The next is the category encoder. It is valuable method in PySpark for converting categorical bracket classes into numerical values. It enables us to handle non-numerical data and prepare it to modeling, and the encoder converts the string values to numerical representation, allowing machine learning models to process the data effectively. Additionally, the decoding functionalities enables us to retrieve the original string values from the numerical representations, ensuring interpretability and ease of analysis. By utilizing these transformation techniques, we aim to optimize the data processing phase and improve overall efficiency and accuracy of our decision tree models. Next slide, please. In our research, we begin by loading the data set sourced from OpenML, containing 1 million data points with 13 feature columns and a multi-class variable with class B1, B2, and B3. We pre-process the data by using vector assembler and category encoder techniques in both SciKit, Learn, and PySpark. We implement the decision tree model using scikit-learn and evaluate its performance using key metrics like accuracy, precision, recall, and F1 score. The results are analyzed to draw insightful conclusions about the model's effectiveness. Next, we build the decision tree model using PySpark, leveraging its distributed computing capabilities for handling large dataset effectively and efficiently. We again evaluate the model performance using the same metrics as in scikit-learn and draw comparison. By combining insights from both implementations, we aim to make informed decisions about the best approach of deploying an efficient and accurate decision tree model for this data set. So, after the rigorous evaluations of the decision tree models implemented using PySpark and scikit-learn, significant differences in the performance metrics we have observed. The PySpark implementation is a decision tree model demonstrated commendable results. Notably, there are no more signs of overfitting or underfitting issues. This indicates the model effectively generalized new data and maintained good balance between accuracy and complexity. The distributed computing capabilities of PySpark likely contributed to the model's ability to handle large data sets efficiently, resulting in the robust and well generalized model. The scikit-learn implementation of the decision tree model exhibited an overfitting problem. The model seemed to be having memorized the training data, leading to decreased performance when applied to learn decision tree on large data sets. While overfitting can significantly impact the model's accuracy and predictive capabilities. From here, my friend Renika will take this.
Results and time. The results clearly indicate that PySpark has a longer total training time compared to scikit-learn. However, the CPU time for training in PySpark was considerably demonstrating the efficiency of distributed computing. In terms of inference time, PySpark outperforming scikit-learn significantly for both the training and test data sets. The inference CPU time for PySpark was also notably lower. These findings the benefits of using PySpark for large-scale data processing and model developments, as it offers improved efficiency and reduced further validating the advantages of distributed computing in the context of machine learning. Change this slide. Conclusion. Our research confirms the performing advantages of PySpark over scikit-learn decision tree modeling. PySpark significantly reduced CPU time and inference time. These findings highlights the importance of distributed computing for efficient and accurate ML model, especially with large data sets. Change this slide. These references have been valuable sources of information for our research on comparing decision tree models using PySpark and scikit-learn. Thank you.
So let me guide you through our project code. Here is the screen where our project is in the Google Colab, and we are giving the bng.wine.arf format dataset from Kaggle, which have 1 million records as you suggested. And we are loading the data here. Maybe we can load there are two options for us. Maybe we can do it from Drive, or we can explicitly load the dataset here, where it will be changed to .csv format, and we'll do preliminary data analysis and start PySpark implementation. If you can see here, if in the 13 feature classes, we don't have any null values present, null or missing values. And we load the data, we do preliminary analysis, and we plot the class distribution chart here. And here B2 is higher than B1 and B3. And and then we are plotting the volume charts here, where we can see the ash feature column is the same in all the classes B1, B2, and B3, where it can be neglected because it won't make a bigger difference in our project. And we'll start with preprocessing with the vector assembly and category encoder, and we split the data for training and testing 80-20, like 80% and 20%, and then we'll create the classifier and we will model it, train the model, and we'll calculate the time there. And here we'll get the total training time and the CPU time, training CPU time. And from then, we'll calculate the total infer time and infer CPU time too for the model performance on train data, and this is for test data. Here is for test data, and here is for train data. Sorry, here is for train data, and here is for test data. And we'll do performance evaluation. We'll get the accuracy, precision, F1 score here, and we'll try to identify the underfitting and overfitting in the PySpark implementation. If we can see here, the Spark implementation has no overfitting or underfitting problem. If we come to scikit-learn implementation, we do the necessary steps to, and we'll convert this Spark data frame to Pandas data frame, and then we'll test and train data sets. We'll get the performance metrics, and if we go down, we can see here we plot the training and testing metrics where scikit-learn implementation of decision trees has overfitting problem, where the train metrics are greater than the test metrics. And if we see the final metrics observation, we can tell that there's a performance difference in terms of both efficiency time, which is our null hypothesis. Though the time to learn is higher for scikit-learn approach, the CPU time is exponentially less for PySpark. CPU time is less compared here. If you can see this, is less when compared to this. So comparatively, model inference time is also uh, exponentially less compared to scikit decision tree train model. Time to learn and time to infer pros that impact of distributed computing in machine learning model development. The results may be vary based on the usage of different hyperparameters on the data. And thank you.